So today, the problem that we're going to do is called find closest value in binary search tree. And the problem reads, write a function that takes in a binary search tree and a target value, a target integer value, and returns the closest value to that target contained in the binary search tree. Now, just an overview, the binary search tree makes this a little bit easier just because it's ordered. And the definition of a binary search tree is that if we're looking at a specific node, let's say 10, all values to the left of 10 are strictly smaller than 10, and all values to the right of 10 are strictly larger than 10. And if we move further down the tree, even in any subtree in this larger tree, we can see that that holds true. So if we're looking at 15, we can see anything to the left of 15 is smaller than 15, so 13 and 14, and anything to the right of 15, in this case 22, is larger than the node we're currently looking at, right? So what this problem is asking is, so you're given a target, in this example 12, and you're asked to find the value within this tree that is closest to 12, right? So looking at this iteratively, we look at 10, right? And we say, okay, well, 10 is two numerical spaces away from 12, right? So let's say this is our closest. And then we say, okay, so if 12 is larger than 10, right? So we know that we don't need to go left, right? Because we'd be moving further away from 12, right? So we say, okay, let's go right. So then we say, okay, 15 is three numerical spaces away from 12. So that can't be our answer. And then we say, okay, 12 is less than 15. So we go left. And then we get to 13. 13 is simply one space away from 12, which is better than 10, which is two numerical spaces away from 12. So 13 becomes our answer because it's the closest value in this tree to our target 12. So really, the best way to think about this problem is it could be looked at as like a tree traversal. So if you're familiar with tree traversals, it can really help in these types of problems. So let's get into the coding portion. So for any like tree problem, they give you a method here, but I like to create like a helper method that has my recursive and my recursive traversal. So let me call it helper method to contain. Okay, and then let's create a variable just to hold our result. And let's name the helper method closest val helper. It's going to consume the tree object that we're given right up here. It's going to also consume the target and it's also going to consume the tree.value. And the reason that we're giving it tree.value is because this object tree that's given to us is the root of the binary tree that we're looking at, right? So in this example, the problem would give us the node value of 10, the tree value of 10, right? So that's where we always start with. And then we are just going to return result, right? Now let's start mocking out our helper method. So public static, we know it has to return an int. Let's copy this value here. BST tree int target, and then int, we're going to call this current closest value, right? Current closest val, right? So the first thing is we need to check for updates to right? So we need to check for updates to current closest val, right? And what this step is going to do is as we make our way through the tree, the binary search tree that we're given, we need to first do a check that if the node that we're currently looking at is closer than what we perceive to be the most current closest value, right? If the tree value, right, that we're currently looking at is closer to our target than the current closest value, then we need to update this current closest val. And maybe it's a little easier if I just show you how to make that check, right? So int now this variable name is a little long, but bear with me. I made it, very long and explicit for a reason. Current closest val, right? So this variable is going to represent the difference between the target that we're currently looking for and the current closest that we perceive to be our possible answer, right? And why I take the difference is because not only is this going to show me how many this statement is going to show me how many mathematical numerical spaces are between the target and the current closest value, right? So that's why you take the absolute value. So it doesn't matter if it goes into the negatives. We're just looking not for the mathematical difference, but we're looking for what is the difference on the number line, right? So that takes the difference of the target and our current closest, right? Now we need to take difference of target and current node, right? And this is just going to be math.abs of target minus tree dot value. All right, and again, this value, this variable is going to represent the difference between the target and the current node we're looking at, right? And then we do a comparative step. So if the difference between target and the current node is less than the difference of target and the difference of the target and the current closest, then we are safe to update the current closest to tree.value, right? And the reason that we're updating this is because, okay, if the difference between target and current node is less than the difference between target and the current closest, we know that this tree value is closer to our target than the current closest value, right? So we update it, okay? Now, we need another step here, right? So again, this is a tree traversal problem. It's going to rely heavily on recursion to make our way through the tree and the subtrees that follow. So let's put a little comment. So let's see. This logic is going to decide if the algorithm should pursue the left subtree or the right subtree, or return our answer, right? So let's say we need to pursue the left subtree, meaning we want to decide if we should go right or we should go left from the node we're currently looking at. And how we're going to decide that is we're going to say if tree.left not equal to null. So basically we're checking that, hey, if we go left, we want to make sure it exists, right? So that's the first check we do. And that space, the target, right? So the number that we're looking for is less than the tree dot value, right? So we're saying, okay, is the target less than the node we're currently looking at, right? So in this case, if the target is 12, we're looking at 10, is 12 less than 10? No, 12 is not less than 10, right? So we know that we wouldn't go left, right? So we're gonna pass in tree dot left. But let's say okay, so in this case we don't go left, right? But let's say we did go left, we would just call this helper function recursively. We'd pass in the tree dot left because we've already checked that it's not null, and we already know from this statement that it makes sense to pursue the left subtree instead of the right subtree. We're going to pass in our target, and we're going to pass in the current closest value, right? Otherwise, we're going to say else if tree dot right is not equal to null and target is greater than tree dot value. Then we're going to return closest helper tree dot right. Okay. And this else if statement is going to be the check to pursue our right subtree. So again, in this example, we start at 10, we say, okay, we check the differences, we're like, okay, everything is fine. So then we have to decide, are we going to go left or are we going to go right? We say, okay, is target less than the tree value, less than 10, right? The node we're currently looking at. Is 12 less than 10? No, 12 is not less than 10. Okay, is 12 greater than the tree value, which is 10? Is 12 greater than 12? Is 12 greater than 10? Sorry. The answer is yes. So then we know that we have to pursue the right subtree, right? Else return our answer, right? Comma. And yeah, and this basically should work. Let's take a look at what we did. So we created a helper method, initializing a variable for our result. This helper method takes in a binary search tree. It takes in our target value, and it takes in a value to help us keep track of what we think the closest value is currently. Based on what we've checked so far, we're calculating the current closest value. This logic, it takes the difference between the target and the current closest, and it takes the difference between the target and the current node we're looking at, right? And then it compares those differences, and whichever value is closer or is less, is the smaller of the two, we want to make our current closest val that, right? Otherwise, we just leave it alone. And then this logic down here, it says, it decides whether we need to pursue the left subtree or the right subtree. It does a null check on both the left and the right. It says, okay, if the target is less than the current value we're looking at, then we know we have to go left. If the target is greater than the current value we're looking at, we know we have to go right. And if all else fails, then return our answer. And let's run the code. Let's see if this compiles. It does compile. We got 12 out of 12 test cases passed. Submit it. And there we go. Okay, and yeah, for this problem, if you study tree traversals, it should be pretty easy. Just the trick in this problem is knowing how to calculate the difference on the numerical line and just do that comparative step. But other than that, it's really just a tree traversal. It does some type of check, then it goes left, then it goes right, then it returns our value. Thank you guys for watching. Hope you liked the problem. Like, share, and subscribe.